Hi everyone, this is Purnima Mahalingam and you're watching video lecture series on field theory. And last video lectures classes we have discussed about Maxwell's first equation, second and third equations. Today we are going to discuss the fourth equation, that is what Ampere's Maxwell's law. Come, let's go to the discussion. Here, what is Ampere's law? What is Ampere's law? So Ampere's Maxwell's law, the Ampere circuit law, is known as the Ampere circuit law. So this law states that the line integral of a tangle, this law says that the line integral of a tangent component of H around a closed path is the same as the net current, that is enclosed current, enclosed by the path. That tangent component of H around the closed path is same as a net current enclosed in the same path. Okay. So in other words, the circulation of a magnetic field H equals the current. The circular of magnetic field H includes the currents. Equals here the closed, in a closed surface, the magnetic field with respect to line is equal to current enclosed in the closed path. This is what an Ampere's law. Here the Ampere's law is similar to the Gauss law and is easily applied to determine H whether the current distribution is symmetrical. The above equation is always holds that whether the current distribution is symmetrical or not, but we can only use the equation determines H with symmetrical current distributions exits. The Ampere's law is a special case of Biot-Savart's law. Ampere's law is a special case of Biot-Savart's law. This is the what introduction about Ampere's law. Here next comes what about Ampere's law? Applying Stokes theorem. So first we are applying the Stokes theorem. What is Stokes theorem? So we can see by applying the Stokes theorem, the left hand side. What happened here? What happens? What happens is the left hand side above the equation. Here what happens there is the left hand side above the equation we obtain I enclosed. What is I enclosed in the closed path, that is line integral of H into dl, that is equal to surface into line integral equal to surface integral of curl of H, surface integral of curl of H with respect to surface. So I enclosed, finally we can write, we can replace this by J. We can replace this by J. So comparing surface integral, we compare these two surface integral, we can get curl of H is equal to J. Curl of H is equal to J. Okay, this is by applying Stokes theorem. Here comes the integral form. Here comes the integral form. In integral form, what happens? We know all the terminology. It's a closed loop line of line, and H is the magnetic field, and that is with respect to line integral, that is equal to I enclosed. The Ampere's current, the electric current in amperes, that is reminds that only the enclosed current contribution, that plus E epsilon naught, that is the electric permittivity of a free space. The epsilon naught, the electric permeability in a free space, that is with respect to time, the difference with respect to time of a surface integral, that is electric flux through the surface boundary by C, that is E vector into N vector, that is with respect to particular area. E vector by N vector with respect to particular area, the rate of change with respect to time. This is what an integral form. Now coming to the differential form, here what happens is that a differential form, what is that? This is what a del operator cross product with respect to magnetic field. The what is del cross product of magnetic field is equal to J. What is J represents? J represents the electric current density in ampere per square meter. The electric flux density, current density in the amperes per square meter plus epsilon naught, that is the electric permeability of a free space. The rate of change of electric flux with the time, that is rate of change of electric flux with respect to time. This is what differential form for Ampere's law. And here we have seen the integral form for Ampere's law. This is a differential form for Ampere's law, and this is the applications of Ampere's law. So what is the application of Ampere's law is this. Here we can see what is what. Application for Ampere's law. Here we have an long straight current carrying conductor. Here what happens here is the magnetic field strength is constant along the path. Magnetic field strength is constant along the path. What happens is North Pole, South Pole, the field strength meters and magnetic path. This is a field meters and magnetic path, and the magnetic field direction is along circular path. What happens here is this, when the distance get increases, what happens? A weak field, we have a strong field. The magnetic field strength depends only on the distance from the wire. The magnetic field strength only depends from the distance of the wire. If the distance get increases, what happens? The strength get the field strength get decreases. So exploring the magnetic field around a current carrying wires. Is a long wires. This is what one of the applications of Maxwell's Ampere's law. Okay, this is the fourth law. And with this, we are closing the Maxwell's 4 laws. And first law, the magnetic field for electric field intensity. Second law is the magnetic field for the Maxwell equation for magnetic flux, electric flux, and Faraday's law, and finally Ampere's law. And thank you so much for watching this video. Hope we can see another video. Thank you so much.